My name is Doug Leaffer, and I'm very pleased to be here today. I teach adjunct at Merrimack College, which is not far from here in North Andover, in the Civil Engineering Department. And my background is in civil engineering and geology. And so the designation you see next to my name is not computer engineering, it's civil engineering. And the PG is professional geologist. So I started as a student, to relate to some of the students here, I started my studies as a geologist about 25 years ago, a little bit more than that, and was always interested in geology as a young child and thought that would make an interesting career. And as it became my career after I graduated, I decided to take a master's degree in civil engineering. They're very complementary because we're studying the earth. We're studying the rocks, the soils, the water systems, the environment, how things are built. Welcome.
Thank you. And
so those two subjects have a lot of synergy together. And engineers that have knowledge of geology really do understand how things work in the earth, in our natural earth, in our natural environment. So it's really quite an interesting combination. And today I'd like to speak a bit about geothermal energy. I'm more of a person who studies the ground and the earth and the systems below ground as opposed to above ground and structures. I'm not a structural or a building engineer. So I'll speak to this topic more from a geo perspective and hope to answer some questions and shed some light on this interesting subject and answer basically how it works and is this something that's workable in this part of the country, because I think there's a lot of folks that think, well, maybe this isn't the right part of the country for this type of an installation or a system, but in fact it is, and it's very efficient and effective. So when we think about heating and cooling air, many homes have heat pumps which are basically extracting air from the outside and bringing it up to temperature or cooling it down to temperature. And in the winter, you're trying to take 0-degree air in this part of the country or 10-degree air and bring it up to 68 or 70 degrees. That requires a tremendous amount of energy and electricity, and so it can be very expensive given the electricity rates in this area. So instead of using the outside air, what geothermal heat pumps do is they rely on ground temperature, which in this area is actually very stable. You all are familiar with the frost line. If you've had anything installed below the frost line, an irrigation system, the temperatures below the frost line aren't subject to the same extreme stress of temperatures from the surface. So they're very stable, and they tend to be in this area about 50 degrees, about 10 degrees Celsius. So rather than bringing air from 0 outside to 68 degrees, and again, you can imagine the amount of energy that would take, we only now have to bring it from, say, 50 to 68. So far less effort and far less energy and far less cost in doing that. So that's basically what we're doing here. And it's also a technology that can use that stable heat below ground to cool homes as well as heat them. So another added benefit is we talk a lot about burning fuel and fossil fuel and releasing carbon into the atmosphere, and that's a very finite resource, the amount of carbon, fuel, oil, and gas that we have on the planet. This doesn't burn fuel like a furnace, not at all. What it does, as I said in the previous slide, is it collects the natural heat through a series of pipes called a loop. There's open loops and closed loops, and we'll show some diagrams in the next few slides. And these are installed below the ground surface, where I mentioned we have a very stable, even temperature year-round, as opposed to the high fluctuations that we get in this part of the world, at least in New England, seasonally. So this is more of an overview of a typical system. This is a closed-loop system, horizontal loop, as you can see, installed in a home. And that green line is the ground surface. So if you think ground surface, grass, green line, below ground is where we have the majority of the components of this system. And then you have in the basement of the home the compressor and distribution system as well. And your loop on the right, that brown circular pattern, it's an odd-shaped pattern, is basically filled with a refrigerant, like ethylene glycol, antifreeze, essentially. And that's circulating through the coils. And what it is it's drawing in heat from the earth and releasing heat as well at the same time. And going through a system of compressors and ductwork, you get that air is brought up to temperature from 50 degrees to, say, 68 or 70 with much less energy than a typical air-driven system, and then released into the room and then circulated back through. So this is a closed loop diagram of a closed loop system. Okay, so let's try to put together an analog as to how these systems work. A great example is up in New Hampshire, the polar caves. Has anyone visited the polar caves? Yeah, it's fascinating. You can be there in July and there's ice in the cave. You know, so why is that? Well, it's stable temperature, very cool, year-round. So in the winter, you're going to actually see in a cave like that a cool temperature, but in the summer it'll basically stay just as stable. So the air underground is constant. It's cooler than the air outside, less subject to fluctuations. And during the winter, it's going to be pretty much the same constant temperature. And that's warmer than the outside air. So this is the basic principle here. You're drawing on that warmth, that reservoir of warmth within the Earth. And if you look even deeper into the core mantle crust of the Earth, I mean, you can see expression of that heat through geysers, volcanoes, some huge processes here. We're not talking about that geothermal energy. That's really a much more macro scale. We're talking about just the warmness itself of the below ground, of the subsurface. So we can draw on that for energy. We can use that warmth for heating and cooling. So any geothermal system needs to have three components. There needs to be some kind of an earth connection, and we showed a loop system in the previous slides. That could be wells or in a horizontal system. Then you need a heat pump, a subsystem in the house, and then a distribution system to actually release that heat or pull that cool from the house and circulate it back into the system. So three basic components. So let's look at the first one, the earth connection. So we're using the heat of the earth as a sink or a source. The sink is a release and a source is a place to pull heat from. And we do that through a series of pipes, which we call a loop, and then buried beneath the ground near a building to be heated or cooled, to be air conditioned or heated. And some of the temperatures that we look at underground could be 45 to even as high as 75. And it tends to be in that zone. Around here we're about 50, 51, maybe a little bit 52. So it's very constant during the year. And that is really the main feature of geothermal, is that we can draw on that constant heat and cool buildings and heat buildings from it, and require far less energy to bring heat up to temperature. So here's a couple of slides of typical systems. And the loop itself can be buried underground horizontally or vertically. You see horizontal on the left. That could be for a typical home, again below the frost line. And on the right is the system that's installed in the new building here. And that is a vertical system where you have a series of deep wells that are drilled, in which you have coils that are installed in a loop fashion to collect the heat from each one of those wells at depth and then relay it back into the building. So they both are similar in principle of operation, except there's extreme depths involved on the right. And we're talking as much as 500 feet deep with the vertical system. So as we saw in an overview slide, the basic system uses a fluid. It could be water, but here in colder climates we use an antifreeze, an ethylene glycol, that is an absorption of heat, acts as an absorber of heat or releaser of heat. So we talked about sources and sinks to the soil. And depending upon whether the ambient air is colder or warmer than the soil, that's where we get either release of heat or absorption of heat. So ambient air is just the general outside air temperature. If I was to say the ambient air in this room, it would be 70 degrees. And so here we have two frameworks of operation. In the winter, we're extracting heat from the outdoor air and transferring it inside, where it goes through ductwork by a fan. And if we have a air-driven heat pump system, we have to crank up the energy to get it from what would be 0 to 68. But with the groundwater heat pump system, we're only getting it from 50 to 68. And in the summer, we have the reverse. The system actually pulls heat from the inside of the building and discharges it into the ground. So this is the loop that we're talking about. And you can use conventional air conditioning, HVAC ductwork to distribute heat or cooled air from the pump itself throughout a building. And here's some twin compressors. I'm not sure where these were installed. I found this photo on a geothermal heat pump informational site, and I think it's just to show you a point of reference. So what's really important to note is that these are very efficient. And if you look at the percentage of energy used throughout the whole system, roughly 70% of that is coming from the ground. That's renewable energy. We're not burning anything. We're not adding any carbon to the environment. It's constant, it's available, and there's no cost to draw it from the ground other than your initial installation cost and obviously your system maintenance cost and electricity required to run the system, but far less than conventional hot air pump systems. So looking at the Earth's temperature, really that's what makes sense. This is very efficient, it's comfortable and quiet. It's a very sustainable technology. We talk about sustainability. This is it's a one-time installation, and you have this reservoir of heat to draw from indefinitely for the life of the components of the system. So some facts, some statistics. According to EPA, geothermal heat pumps are now listed on the Energy Star program. You've all seen appliances that have an Energy Star rating, which means they have more efficient operation, they use electricity. Geothermal heat pumps are now rated under that system, and the EPA has estimated that you can realize, or users of geothermal heat pumps can realize, some 30 to 40% lower on their energy bills. In fact, I think there's a display outside today of a couple that have geothermal and solar in combination, and I asked them what their heating bill was, and I believe they said it was $2,500 for the year. So the other beauty of these systems is they're very simple, mechanically simple, and the outside components are below ground. So once they're installed, that's it. They're protected from weather, they're protected from damage, and maintenance costs for these systems are really limited to the interior components and would be lower versus other conventional systems. So here's something that I found, which is in Oklahoma City. I looked for something locally, but I couldn't find anything as an example. This is a 3,000 square foot home, and their average electric bill is $60 a month using geothermal heat pumps. So very cost effective. This is very much in line with the folks that we talked to outside. So in this part of the country, the ground temperature would be probably in the 60s. Below ground, the groundwater temperature would imagine probably approaching 70. So you can consider that as even, it's a different reservoir of heat, unlike here. If you have to cool that, then it's actually probably very efficient to do that. So we talked a little bit about costs and energy costs and how much bills are per year. You really have to consider a few things. The cost of drilling is a capital cost that needs to be, an upfront cost that needs to be considered. And so that has to be added to the project. And we're talking about deep wells in some cases, 4-inch wells, diameters. This is the expensive part of the project. The final cost is going to depend on vertical deep installation or a horizontal, as we showed in those diagrams, whether it's looped or whether it's very deep. And in this case, for North Shore community, we have a closed-loop vertical system with 25,000 linear feet of wells, and so across 60 wells. So we're talking about just roughly about 500 feet each. These are typical well depths. So these are drilled deep into bedrock, and the temperature of the formation around here is about 51, which is a typical groundwater temperature. It's going to stay that year-round. It might fluctuate a degree up or down. That's why this is so effective. There's not a lot of variance here. It's very stable at that depth. And I have a statistic on thermal conductivity, 1.5 BTU per hour per foot per degree Fahrenheit. So those that know something about energy can do the calculations and realize what kind of energy you can get out of this type of installation. And the rock itself is called rhyolite. It's like a granite, essentially. And that's first encountered about 140 feet below ground surface. So above that is fill and glacial till and other materials. And of course there's a water table. But we're trying to draw from that heat in the reservoir of heat in the rocks. And that's what we're doing here. And so, yeah, we're coming to a close. And another crowd is getting ready to do a tour. So thanks for your attention, and I appreciated your time and your comments and your input.